So those models are exclusive models to regression and classification. Now the models that we are going to discuss from here on will be both regression as well as classification model. We call them as CART models. Within the CART models, the very popular models are tree-based models. Tree-based models. Tree-based models. Also, there are multiple models here. Single tree model. We call it as decision tree. Single tree model, the decision tree. Decision tree is a tree-based model. It will be having a root node, then it will split into two nodes, then decision node. A decision node will further split into decision nodes, or it may split to end node or terminal node or leaf node. So decision tree is a tree-based models are very popular in decision, what you call machine learning and data science. So this is a structure of a decision tree model. There will be a root node on top. The root node will split into decision nodes. The decision nodes will further split into a decision node, or it will split into a terminal node or leaf node. Root node will be splitting into decision nodes. The decision node will further split into decision nodes, or it will split into leaf node or terminal nodes. Leaf nodes are also called as terminal nodes. So this is a structure of the decision tree. So single tree model, decision tree. The output of this model will be a decision tree that looks like this. The output of the model will be a decision tree that looks like this. So decision trees are very powerful algorithms within the data science framework. They both work on regression data. They also work on classification data. Okay, so let us further understand the decision tree are binary splitting trees. What do you mean by binary splitting? Binary splitting. Yeah, that means only two. Only two, 0 and 1 binary. 0 being no, 1 being yes. They are binary splitting. There is only two splits at every node. Binary splitting trees at every node. At every node, they will split into the binary splitting except the leaf node or the terminal node. Leaf node is also called as terminal node, that is the end point of the tree. A decision tree will have a lot of subtrees. A decision tree will have a lot of subtree. When we call it a subtree, when there are terminal nodes in that tree, or when there are leaf nodes, like in this case, you can see here, the tree is ending here. There is no further propagation. The tree is ending here. This we call it as a subtree. Now this whole thing we call it as a subtree because it is ending here. Similarly, in the real time, when you're building with large scale data and many variables, it will be a very, very large tree with multiple subtrees, sub branches. There will be subtrees and subtrees. So a lot of these trees will be generated using this methodology. Now, decision trees are binary splitting trees. They will only split into two at every node. They are also recursive partitioning trees. They are also recursive partitioning trees. As the tree splits on previous node number of observations not on total number of observations. And once all observations are allocated into leaf node or terminal node, the tree growth will stop. The tree growth will stop. Recursive partitioning trees. So the tree will split on the previous node number of observations. So as the tree splits, the root node will have all the observations. Root node will have all the observations. The first split will split the observations into two. Say root node has 1000 observations. On the first split, it split on left side 400, on the right side 600. This 400 will further split into 150 and 250. This 600 will split into 150 and 450. This 450 will further split into 200 and 250. So as the tree goes down, the number of observations will come down. So that is the advantage, or that is what I mean by recursive partitioning trees. As the tree grows down, the total number of observations will reduce. And once all the observations are classified into the leaf node and the terminal nodes, that growth will stop. That is the end of the algorithm. The tree growth will stop. So this is what we call as recursive partitioning trees. Recursive partitioning trees are, there are non-recursive trees also, but the one which we are going to use in machine learning in data science is recursive partitioning trees. No, these are classifications. Non-recursive trees are, you have your chi-square based trees, shade trees are there. Then you have trees like which are what you call something related to boost, ADA boost trees, ADA boosting and all are there. So there are some trees which are non-recursive in nature, but most of them are recursive. So the structure of the decision tree is we have the root node, this is the top node. Then we have the decision node on which it splits. Then we have terminal node or leaf node, which is the end point of the tree. End point of tree. Okay. So decision trees are so decision trees work with large scale data, work with missing values and outliers, and also work as unsupervised learning algorithm as it gives part of output as it gives part of output variable importance. It gives variable importance as part of the output. Variable importance also called as feature importance. All right. Now let us look at the tree splitting methods. The tree splitting methods are very important. On what basis the tree will split? One of the default method is Gini method, also called as Gini impurity. The formula is 1 minus sigma probability of I, 1 minus sigma probability of I to the power of 2. 1 minus sigma probability of probability square. This is the default method in most of the softwares. Default method in all the softwares. Because it is easy to calculate. Because it is easy to calculate. Lowest Gini is, Gini is calculated for all variables with the dependent variable Gini is calculated for all variables with the dependent variable. Then lowest Gini is the first split and ascending order till 0.50 and Gini greater than 0.50 will not be considered in the tree. The variable that has Gini greater than 0.50 will be dropped from the tree. The next is entropy and information gain. entropy and information gain method. Entropy is equal to sigma minus probability of I into log second base probability of I, log base 2, log second base probability of I, minus probability into log second base of probability of I. This is the formula for entropy. Information gain is equal to entropy of dependent variable minus entropy of independent variable. Entropy of dependent variable minus entropy of independent variable. Entropy and information gain calculated for all variables with the dependent variable and highest information gain is first split and descending order till 0.50. Information gain less than 0.50 deleted from the information gain less than 0.50 will be deleted from the tree. So entropy and information gain. The next set of splitting method techniques is entropy and information gain. Entropy formula is sigma minus probability into log second base of probability. And entropy and information gain is calculated for all variables with a dependent variable. Highest information gain is the first split and descending order till 0.50. Information gain less than 0.50, the variable will not be considered in the tree or the variable will be deleted from the tree. It will not be considered in the tree, anything less than 0.50. So that is one way of eliminating variables which are found to be non-significant. If it finds some variables non-significant, automatically they will not appear in your tree. So these are the formulas. Okay. The output is a decision tree. The output is a decision tree diagram or plot. What was the output in regression, multiple linear regression and binary logistic regression? We get an equation. The output of a multiple linear regression and binary logistic regression is an equation. And using that equation, we will create predicted values and predicted classes. Now, in this case, the output is a decision tree diagram or decision tree plot. Based on the tree, rules are created and rules are used for prediction. So this is a rule-based prediction. So what happens is, once the tree is created, we will create rules. And the tree must be read top down. Tree must be read top down, not bottom up. It has to be done top down, and it will create rules. If the person age is greater than 40 and his gender is male and his income is greater than 50,000, then he buys your product. If the age is less than 40 and he is female and his income is less than 30,000, she will not buy. So these are the rules which are created from the tree. The tree will be read top down and each branch of the tree will be read. A rule will be created. From each branch of the tree, a rule will be created using if and then, or when else then. They have this type of rules which can be created from the branches of the tree. A complete branch right from the top till the leaf node, it will be created as one single rule. Like that, multiple rules will be created, and using these rules, it will predict. Now, these rules we can't see in Python, but in our software we can see the rules also. So I'll try to show the rules also. What are the rules which are there for that particular model? Okay, so that is how we will look at it. So it's a rule-based prediction. It's one of the common interviews. How does decision tree predicts? It creates rules based on the tree, and it uses these rules to make prediction. Now, there are many advantages of decision tree. It works with outliers, it works with missing values, it works on large data. It requires low computing power. A lot of advantages are there. But the biggest disadvantage, or the only disadvantage, is no, not time efficiency, overfitting. Biggest disadvantage is overfitting. Overfitting means too good to be true. Like you will get 100% accuracy, right? Close to 100% accuracy and close to 1 R squared. We have defined certain ranges, right? 0.70 to 0.95 for classification model. Anything above 0.95, we call it as overfitting. We also have such restriction for R square. R square must be between 0.60 to 0.95. Anything above 0.95, we call it as overfitting. Below the threshold, we call it as underfitting or model failed. Above also model failed. Overfitting is also a problem. What happens in overfitting is your trained model will have good score, 99-100%. But when you rerun the model with test data, its accuracy drastically falls to 70% or sometimes less than 70%. Or when you run the same model 5 times, the accuracies will drastically change. That we call it as overfitting, which is a problem in data science. Overfitting is a problem in data science. So decision trees are prone to overfitting. Decision trees are prone to overfitting. Now, to control overfitting, we have to use max depth of the tree. Max depth means how many layers you want in the tree. 1, 2, 3, like the splits, right? Subtrees. How many subtrees you want? 1 subtree, 2 or 3 subtrees, like that. You can fix the depth. Using the max depth, we can reduce the overfitting. See, the larger trees will definitely overfit. Larger trees will definitely overfit. So we have to bring them, or we have to reduce the depth or the layers in the tree. Thereby, we can control the overfitting aspect of the decision tree. By default, in 99% of the times, it will overfit. By default, it will overfit. So how do we control the overfitting? By fixing the depth of the tree, by making max depth is equal to 6 or max depth is equal to 8 or max depth in some cases 12. Sometimes like that, we give different max depths and then we try to build a model that has the low overfitting problem. So that is what we need to understand for decision trees. So they are very powerful. They take less computing power. They are easy to compute. They are easy to understand. You can easily understand them also. You can easily interpret them also. So they are very, very interesting algorithms in data science, which work both as classification and regression algorithm, and also as unsupervised algorithm, because as part of output, it will give you variable importance or feature importance is also given. So this is the theoretical backdrop of your decision tree models. Okay.
Part of they do classification and regression, right?
Yeah.
So classification and regression individually are it comes under the category of supervised learning.
Yeah.
Why is decision tree not supervised learning?
Why is decision tree?
You said it also works with unsupervised.
Yeah, because it gives a variable importance. Because see, once you know the variable importances, it becomes a supervised problem. The fundamental assumption of unsupervised learning data is you don't have any understanding of the variables. You don't know which variables are important, which variables are significant. Until unless you know the variable importances, you cannot build a model. That you will come to know once you build a decision tree.
So variable importance is learned as we go. Like
it uses the Gini and the entropy only. From the Gini and entropy only, it will identify the important variables. And some of the variables it eliminates from the tree based on the Gini being greater than 0.50 or information gain less than 0.50. Such variables anyway, it will remove it. So finally, you will get significant variables. Now, once you get the significant variables, you can go back and convert it into a supervised learning problem, and you understand these variables further by doing an EDA, and then you build your model. I've sent you the sheet. Okay, all of you got the sheet. Okay, all of you got the sheet. Now we have data here, 4 independent variables, variable A to D, and a dependent variable, variable E. The dependent variable A is in binary format, positive and negative. Okay, so we will first do the Gini calculation, and then we will also do the entropy calculations to understand how these formulas will work. A, B, C, D are the independent variables. Variable E is the dependent variable. Dependent variable has 2 classes, which is a binary problem, positive and negative. Now, our data is numerical in nature. And I told you that decision trees are binary splitting. That means you have to convert the data into a binary argument. How does the data will be converted, numerical data to be converted into binary argument? Let us say variable A. What is the lowest value of variable A? I think it is 4.7. The highest value is 7. So what the algorithm will do is it will randomly pick a value within this range. It will randomly pick a value within this range and uses this value as a logical operator like this. So we have positive, negative, the two classes in our dependent variable, and then greater than equal to 4.2, less than 4.2. A random value within the range will be taken. A random value within the range will be taken. Here we are taking as a 4.2 as a random value. Now I am calculating the Gini for variable A. E is the dependent variable. A, B, C, D are independent. E is the dependent variable. Anything, it will take any value which is randomly chosen within the range. Now, you might think it will be, if you take equal to mean, the problem is it won't split properly. So it randomly picks a value within the range which is closer to mean or somewhere between mean and median. It will, it means it is in the range of 5.2. Sorry. 4.7 to 7. 4.7 to 7. And if you take the average is how much? 5.58. And if you take the median, it comes to somewhere around 5.3 or something like that. It will take a value which is closer to range or in between range and median. What is the median? .3. Okay, median is 5.3. Mean is 5.58. So somewhere it is taking closer to median in this case. 5.2, let us take it randomly picks a value of 5.2. Now, how many positives are greater than greater than equal to 5.2? These are the positive. How many of them are greater than equal to 5.2? 1, 2, 3. 3 are there. Less than 5.2 and positive. 1, 2, 3, 4, 5. Within negative greater than 5.2. 1, 2, 3, 4, 5, 6, 7. And less than 5.2 in negative 1. Positive and negative are the categories in the dependent variable. Positive and negative are given in the problem statement itself. They are the dependent variables, positive and negative. Like yes or no. Now you have to find out how many in the positive category are greater than equal to 5.2 and how many of them are less than 5.2. Similarly, in the negative category, how many of them are greater than equal to 5.2 and less than 5.2. You have to count. This is simple counting operation. right? Now we will calculate Gini of 3, 7. Gini of 3, 7. 1 minus sigma probability square. 1 minus sigma probability square. What is the formula for probability? Number of events divided by total number of events. Probability formula is number of events divided by total number of events. 1 minus sigma probability square is equal to 1 minus open 2 brackets. Probability is 3 by 10 close bracket to the power of 2 plus open bracket number of events is 7 divided by total number of events is 10 to the power of 2 close 2 brackets. Close 1 bracket only. Is equal to 1 minus open 2 brackets 3 by 10 whole square plus open bracket 7 by 10 whole square. Gini is equal to 1 minus open 2 brackets 3 by 10 whole square plus 7 by 10 whole square. So you got Gini of 0.42. Similarly, Gini of 5, 1. Gini of 5, 1 is equal to 1 minus open 2 brackets 5 divided by 6 to the power of 2 plus open bracket 1 divided by 6 to the power of 2 close bracket. So what is you got Gini for 5, 1? 0.27778. One minus sum of probability square. Now, Gini of variable A would be weighted average. Gini of variable A is equal to 0.42 into 10 divided by 16 plus 0.2778 into 6 divided by 16. Weighted average 0.42 into 10 divided by 16 plus 0.2778 multiplied by 6 divided by 16. Weighted average. It's not sum product. It is multiplication of weights. In some product, you add, multiply and add. Here, it's not that case. There you have two different arrays. Here it is not arrays, right? Formula is this one, 0.42. This one, right? This one, right?
Yes.
This one is 0.42 into 10 divided by 16. 0.278 into 6 divided by 16. 0.42 into 10 divided by 16 plus 0.2778 into 6 divided by 16. Okay, so Gini of variable is 0.3667. Now let us calculate Gini of variable C. Greater than equal to 3.2, less than 3.2. Some value I have taken within the range. So greater than equal to 3.2 within the positive range, 0. Then how many of them are less than 3.2? 8. In negative, greater than equal to 3.2, all of them, right? So this is coming as a full leaf node. Huh? And make it 4.2. Because we want at least one branch to left out. This is 8, no problem. Greater than 4.2 and negative, you have 1, 2, 3, 4, 5, 6. And this is 2. Got it? Gini of 0, 6, you don't need to calculate, it will be 0. If one of the value of Gini is 0, it will be automatically 0. Even if you calculate, the output will be 0. 0 of one of the values 0 is 0. And Gini or entropy of equal classes is 1. Gini or entropy of one value being 0 means output will be 0. Gini or entropy if both the classes are equal, that means you got equal 8, 8 or 4, 4, then it will be equal to 1. So we have to calculate only one Gini here, Gini of 8, 2, which is equal to 1 minus open 2 brackets 8 divided by 10 to the power of 2 plus open bracket 2 divided by 10 to the power of 2 close bracket. You got 0.32. And then calculate the weighted average. Zero into 6 divided by 16 plus 0.32 into 10 divided by 16. What 0.20 as Gini. So if you compare these two, the tree will first split on variable C. And what will be the conditional logical operator greater than or equal to 4.2. So this is the process of Gini calculation, which is done in decision tree for classification. Got it, all of you? Gini calculation. You can do for PNT also. Any variable you can do. Want to do it for B or D? So calculate Gini for variable D. D. You can take greater than or equal to 1.2, less than 1.2. Calculate for variable B. Got it? So how many greater than equal to 1.2 positive? 0. Negative? 7. Less than 1.2 positive? 8 and 1. Gini of 0, 7 is 0. 0.11. So variable D will be the first split. The root node split जो होता है ना, that is called the first split. So the first split is variable D greater than equal to 1.2, yes or no. Yes onto the left side, no onto the right side. Next would be less than 1.2 side, variable C. So it will be like this. You can calculate for B also. You can calculate for B also. So this will be variable D, right? And what is the logical test we are using? Greater than equal to 1.2, right? So let me make it center, right? This side it will be yes. This side it will be no, right? Now on the greater than equal to 1.2, 4. This is 4.2, right? Sorry, 1.2. On the greater than equal to side, it is 0. So this will be a terminal node. Now the next split will happen here. This side, that side it will end. The next will be this side. So what will be this variable? Variable C. And what is the logical test? Greater than equal to 4.2. On the left side, yes. Yes is 0, right? So yes. Okay. Now, if you calculate B, the B will come this side because this is again terminal node, right? This is again endpoint because endpoint means if there is a 0, that becomes a terminal node. If one of the Gini values is 0, it becomes a terminal node or endpoint. There will be no further growth of the tree on that side. So in this case, greater than 1.2, we have 0, right? So if it is yes, it becomes a endpoint. That means it becomes a leaf node or a terminal node. The tree will go on the other side. This will be the decision node. This will become a decision node. The variable C decision node again will split into two. This again becomes a terminal node or leaf node. This is again a decision node. On this node, you will have B. B might also give you a terminal node and a normal node also, or a decision node also. If you have to calculate, you can calculate for B also if you want. This is how the tree is built. Got it?
Decision that we got is for category positive. The same we are looking for category.
Pardon?
So the tree that you got is
Ah.
for category value positive.
No, no, both positive and negative. So see here, this is positive 0, right? So what will be this? Negative. Here also positive is 0. So this will be the decision, the terminal node will be negative because positive is 0 in both the cases. So we'll have only one value, which is the negative value, right? So this is a negative terminal node. That means let us say the tree will be like this. If variable c is greater than equal to 1.2, then the prediction is negative. If variable greater than 1. If it is not greater than 1.2, then variable c is yes, then it will become negative. Or if variable d is not greater than 1.2 and variable c is also not greater than 4.2, then a decision node is there which will go to B or A, and then it will propagate. Right. Whereas if the variable d is greater than 4.2, is not greater than 4.2, and variable c is less than 4.2, the final prediction is negative. The final prediction is negative. So this is what happens because there are no positive predictions here. What predictions we have? We have only negative predictions. So this is what the tree will look like. So ultimately you have leaf nodes of both negative and positive. The classes will appear at the end. Okay. In the end, you will get the classes. In between, you will get only the independent variables. Then it will become decision node. So calculate for B. So we will take B as greater than equal to 2.5. For B, we will take it as greater than equal to 2.5, less than 2.5. Got it? What are the values? Positive 8 and 6. Then 0 and 2. 0.42, right? So this might be thrown out of the tray because it is above 0. We said 50, right? Okay, you can keep it, no problem. So the next split will happen on variable A. So variable A, what is the test? Greater than equal to 5.2, right? So both sides, we got the nodes. Three point seven, 3 and 7, 5 and 2. So this will be a decision node, variable A. Yes side, how many we will get? 6. And no side, we got 10. Yes side, we got 6, and no side, we got 10. Right? Observations in terms of categorization, 6 and 10. Sorry, it's not 6 and 10 here. 10 and 6, yeah. So S is greater than equal to 5.2, 10. Less than 5.2 is 6. Now it will go to which node? It will go to this node. 10 is this side, right? So this will go, the variable V will come onto this side. Greater than which row has the highest observations? Actually, there is some error we are getting. Actually, the number of observations should be equal. We're not getting equal thing. Yeah, see here. There are students in the class, half of them play cricket, half of them do not play cricket. Then they use the split variable less than 5.5 feet and greater than 5.5 feet. Okay, that is the split variable. 8 students, 2 play cricket, and 12 students, 8 play cricket. 4 of them don't play. Okay, so here out of 8 students who are less than 5 feet, only 2 will play cricket. And out of 12 students who are greater than 5.5 feet, 8 of them will play cricket. Right. Now, you can see here, most of the people within the greater than 5.5 criteria are playing cricket. Very less of them are not cricket. So then, if you see the performance class, above average and below average in their marks, classroom performance. 14 students, 8 of them are performing well, 6 of them are not performing well, below average. 6 students play cricket. Sorry, 2 students play cricket, 6 students out of 6, 2 will not play cricket. So based on this, the class splitting will happen like this. Okay, where is the split one? There is an algorithm where we can see the splits clearly. So based on gender and 10th and class, For gender 0.59, for class 0.51. So the note will split on gender. Where is the split mechanism? How come I forget? Hello? Hello? Good morning, Chapali. అది నిన్న కాల్ చేసినమ్మా, ఆయన అవైలబుల్ లేరు కదా, డాక్టర్ చంద్రచూడ్ గారు. నేను వస్తాను తర్వాత. రాజేష్ ప్రభాకర్. రాజేష్ ప్రభాకర్. So it will go to the maximum value and then it will split. Na? 14 and 10 are there. Actually, it should be equal. So this would be variable A, right? Ten and 6 we have. This is 14 and 2. Okay. The majority side is 10, right? This side it will split. And this will be terminal node. And further splitting will happen on this side. And again, you will get terminal nodes here. This will be the end of the tree. So this is the final structure of the tree. Actually, the values are not matching here. Generally, the values match. The previous node values should match. Let us see. Maybe our splitting criteria, there is some issue. That's why it is not taking it properly.
So which way to match?
The number of observations, it's better to match. Node observation should be significant. I'll tell you actually, there was an article where we could see the splitting. I'm not able to get it. Okay. So once we run an example, then we will see how it actually fits. Okay, so we'll take a break and we'll come back and also work on entropy. Project on. enter, एक second. One second. Hey, anybody has a pen? Just give me a pen. 1 second. Sign the. Here. All right. So, we will resume the recording. Yeah. So pre-break, we have calculated the Gini. Now let us, for the same tables, the tables will not change. You have to calculate entropy. The tables will not change. It will be the same tables. Control C, Control V. Instead of Gini, we will calculate entropy. No, error rate is residual, RMSE. So entropy is a splitting method. Okay, all of you have created the copy paste to the table. Now, entropy of 3,7 is equal to -1 into open two brackets 3 divided by 10 multiplied by log open bracket 3 divided by 10 comma base 2 plus open bracket 7 divided by 10 multiplied by log 7 divided by 10 comma 2 close two brackets. So -1 into 3 divided by 10 into log 3 divided by 10 comma 2. Comma 2 means second base. Plus 7 divided by 10 into log 7 divided by 10 comma 2 minus probability into log second base of probability. No. Log base 0. 1, 2, 10, you can go up to 10, log 10, base 10. So you got 0.88, right? Entropy of 5, 1 is equal to -1 into open two brackets 5 divided by 6 into log 5 divided by 6 comma 2 close bracket plus open bracket 1 divided by 6 into log 1 divided by 6, comma 2. You want the font size to be made a little bit bigger so that you can see. This is the formula. No, we have to calculate weighted average. Huh? We have to calculate entropy of variable A, which is again weighted average, is equal to this into 10 divided by 16 plus this into 6 divided by 16. So you get 0.7925, right? Now, in dependent variable, what are the dependent variable classes? Positive, negative. So we have 8 positive and 8 negative, right? Entropy or Gini of equal classes is always equal to 1. Entropy of equal classes is 1. So, information gain for variable A, information gain for variable A is equal to entropy of dependent variable minus entropy of variable 0.20. So this variable will not be part of the tree. That is the weighted average into 10 by 16 into 6 by 16. The values into 0.8812 into 10 by 16 plus 0.6500 into 6 by 16. So entropy of dependent variable is 8,8 is 1. So information gain of variable A is equal to 1 minus entropy of variable A. You will get 0.20. Now we can calculate entropy of variable C. Okay, got it? So entropy of 0, comma 6. No need of calculating, it will be 0. Entropy of 8, comma 2. We have to calculate is equal to -1 into open two brackets 8 divided by 10 into log 8 divided by 10 comma 2 close bracket plus bracket 2 divided by 10 into log 2, sorry, 2 divided by 10, comma 2, close to brackets, 0.72. Okay. So entropy of variable C is equal to 0 into 6 divided by 16 plus 0.72 into 10 divided by 16. So 0.45. Information gain of variable C is equal to entropy of dependent variable is 1 minus 0.45, you get 0.54 as information gain for variable C. So entropy of dependent variable minus entropy of variable is your information gain. Entropy of 8, 8 is 1. Equal classes is 1. If one of them 0 is 0. All right, all of you got this? Okay, all of you got the calculations? How Gini and entropy information gain are calculated? Now, in case of regression, the calculations are quite different. We have standard variance reduction, which is used for calculating the doing the calculation in terms of regression problems. So in the regression sheet, I have given you what variables? Just tell me what variables I have given. Hours played and outlook, right? Hours played and outlook. So first we need to calculate the standard deviation for one attribute, which is the this one. You know, simple standard deviation calculation, right? So 9.32 is the standard deviation. You can calculate it if you want. This, let me just move it here, is equal to STD EV, and then you select the hours played. Oh, we got different standard deviation. There are number differences are there, 25, 30, 48, 46. Okay, the numbers are different. Okay, so 12.4 is a standard deviation. This is the standard deviation. Now, coefficient of variation. The coefficient of variation is standard deviation. We have to calculate the mean also. Average is equal to average of the hours played. So coefficient of variation CV is equal to standard deviation by mean into 100. So standard deviation divided by mean into, or we'll convert it into percentage, 0.28. Click on the percentages, and 28.87 is the coefficient of variation. You know how to calculate standard deviation and mean, right, in Excel? Okay, so you have to first calculate the coefficient of variation. Then we have how many categories in Outlook? We have how many categories in Outlook? We have rainy, we have sunny, and we have overcast, right? We have three categories: rainy, sunny, and overcast. Then standard deviation of hours played. We need to get the standard deviation of hours played. And also we need to get the count. Standard deviation of hours played, and we need to get the count also. So apply a filter, go to Outlook cell, go to Home tab, sort and filter, apply filter. On the Outlook, apply filter. Go to Home tab, select the Outlook header and apply filter. Home tab, sort and filter, click on filter. Okay. Now go to the Outlook filter, unselect all, click on overcast. Click on overcast. How many things are there in overcast? 3 are there. And what is the standard deviation? You have to get the standard deviation is equal to STD EV of these three. 11.04. Standard deviation of overcast is 11.4. And how many observations we have? We have 3. Similarly, I'll change the overcast to rainy. Rainy, how many observations we have? 6. We have 6 observations in rainy and is equal to STD EV. We will calculate the standard deviation. Similarly, I'll unclick rainy, I'll click on sunny. Sunny, how many we have? 5. And then is equal to STD EV, we will calculate the standard deviation of the 5 observations. Right? And then I'll go and select all. So we got the
Taking the range of all these values.
Which one?
Taking from 27 to 27. Some 10 numbers. Only 3 numbers, right?
No, no. Actually, we have done.
For sunny also, some complex for sunny also. So you take one value, comma, the other value, comma.
Oh, that's why it is giving an error. Huh? Let me just check. Overcast, right? We got 3 values. Control C. I'll paste them here. Paste values and under formatting. Is equal to STD EV of these 4 values. 2.64. Yes, you are right. You are right. So, Control C. Thank you. You have corrected the mistake. Then, paste them in the separate place and then calculate. Na? Copy them down. Control C. Paste as values. Now, is equal to STD EV. Select the values. 13.14, right? 13.14. Control C for rainy. Paste values. For sunny, I'll copy these values. Control C. Paste them as values. is equal to STDEV 15.46, right? Is this right? 15.46. Yes. Right? 13.14, 15.46, and this is 2.64. Okay. Now we will calculate standard deviation of hours played, comma, outlook. Probability is, the formula is S of comma, sorry, S of H comma HP comma outlook is equal to sigma. Sigma probability of C multiplied by probability of I multiplied by segment of I. Sorry, standard deviation of I. So probability of I into standard deviation of I. That means is equal to open bracket 6 divided by 14 multiplied by 13.14 plus open bracket 5 divided by 14 into 15.46 plus open bracket 3 divided by 14 into 2.64 at 11.72. Okay. So standard variance reduction for HP, O, hours played and outlook is equal to standard deviation of hours played minus this 0.31. Probability into multiplication standard deviation. Probability 6 by 14, 5 by 14, and 3 by 14. Got it? So probability is nothing but number of events, count of events by total events. 6 by 14 multiplied by standard deviation, which is 13.14. Same thing, 5 by 14 multiplied by standard deviation. Similarly, 3 by 14 multiplied by standard deviation. So you got standard variation reduction of 0.31. Now, like this, you will calculate all the numeric variables with the dependent variable, and then you will get the final standard deviation reduction. And the variable that has the least standard deviation reduction will be your split variable. So the variable that has the least standard variable reduction will be your first split variable. So like this, it will calculate for all the other independent variable might be play or not play. Based on these things, dependent variable will be play and not play. So we have to calculate between that and also hours played. Hours played is a numeric variable, categorical dependent variable, it might be there. Or in this case, regression means hours played is dependent variable. Hours played is dependent variable. And then we use weather condition like outlook, whether they have played or not. And we will use other variables like, lighting, whether the light was good or bad. Like that, we will use some variables to predict the number of hours played. So when you're using decision tree as a regression model, the calculation is quite complicated using the standard deviation, variance, reduction we have to work upon. Which one? Standard deviation minus standard deviation of the probability. Sorry, standard deviation into probability. Of hours played. Okay, any doubts on calculation? So for implementation, you can open the analytics with the, let me, HR analytics, where we have run the logistic regression. Open the analytics with the, where we have run the HR analytics thing. Okay. Run all the cells. So from sklearn, dot tree import decision tree classifier. Tree is equal to decision tree classifier null brackets. Tree model is equal to tree dot fit x comma y. Pre-model dot score x comma y. See, overfitting 99.97 accuracy. So we have imported the decision tree classifier and we ran it on the HR analytics, where x is your independent variables, y is your dependent variable, is underscore promoted, yes or no. Okay, so we can see here the score accuracy is 99.97, which is overfitting. Now, why I'm calling it as overfitting? If I run the model 5 times, hello? Yeah, hello? Yes? చెప్పమ్మా దేని మీదమ్మా దేని మీద అది ఆల్రెడీ సెల్ అయిపోయిందమ్మా కొత్త వెహికల్ తీసుకుని 2 months కూడా అవ్వలేదు కొత్త వెహికల్ తీసుకుని 2 months అవుతుంది లేదు 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 from sklearn dot model selection import cross val underscore score. Cross val underscore score x comma y comma 3 comma x comma y comma cv is equal to 5. So I am building 5 different models. I am building the 5 different models, or I am running the model 5 times. On each iteration, see, first iteration, the score fell down from 99 to 90. Second iteration, it came down to 89. Third iteration, it came down to 89, 89, 89. So if you take the average of all the 5 scores, it will be around 90%. Whereas your training accuracy is close to 100%. Your training accuracy is 100%. But if you repeatedly tested it again 5 times, this process we call it as cross validation. Cross validation means repeated testing. Repeated testing of the model with same data. So I have tested the model 5 times repeatedly with the same data. I got different accuracies which are less than the original train accuracy. But actually this is not that bad, but sometimes you'll get 70%, 60%, worst accuracies you'll get. In this data, you're not getting it. This is comparatively better. 99 and 80, 99 is okay. But in some cases, you'll get 70%, you get 65, sometimes you'll even get 45% also. So that sort of very bad accuracies will come. So this is the problem with decision tree. Overfitting. Overfitting is the problem that we have with decision tree. Now, how do I reduce the overfitting? By fixing the max depth. I am reducing it to max depth is equal to 8. See, the accuracy came down to 93. Now look at the accuracies. All of them are closer to one another. I have reduced the depth of the tree to 8. 8 levels tree. 1, 2, 3, 4, 5, 6, 7, 8. Not beyond 8 levels. So you have an 8 level tree. The train accuracy is 93%. Test accuracy is also 93%. This is the best model. On repeated testing also you get the same accuracy, right? So by controlling the depth of the tree, you can eliminate overfitting. How do I get the depth of the tree? Generally, we start with 6 and 8, multiples of 6, 8, 12, like that we'll go. And then we will give those values and then we will test the model and we'll get the final thing. It's all about trial and error. So when I built a tree with depth of 8, I got a train accuracy of 93.50. And when I did a cross validation means repeated testing of the model with the same set of data 5 times, I got almost similar accuracies. So this is the best fit model. This is the best fit model. Whenever you do decision tree, you always work with max depth. You have to set max depth, otherwise it will be overfitting. Or you build a model first and then go back and set your depth. And according to the requirement, you will change the max depth and you will get the best fit model. So decision tree is one of the best model. Only problem is overfitting. To control overfitting, we have to just reduce the depth of the tree. Once you give the reduce of the depth of the tree, here everything is perfectly done. No overfitting, nothing. Even the accuracy is a good accuracy. And the cross validation is also very close to the original accuracy. Got it? Now, to see the tree, if you want to see the tree, from sklearn dot tree import export underscore graphics. Export underscore graphics tree model. Okay, we got the tree model, but tree is not coming. Let me just see. There's this type of tree we should get. This guy has used a good one. Let me just check what is the package he has used for the tree. Okay, from sklearn.externals.6 import string IO. Classifier. Let me see if I can get this tree model running. Sorry. Is pointing to no module sklearn.externals.6. So, not find. Not find satisfaction requirement. Okay. You're getting the text version, but why are you not getting the pure graph? Actually, we get the tree actually. Hmm. Output file will be the dot file, where you'll get the Word document. The same output, what you got here, na? The same will come in the dot file. 1 second, let me check. Okay, we are not getting the tree here. Scroll on the tree. Plot underscore tree is there, yeah. Shit. Plot underscore tree is also there. So export graphs to is comma plot underscore tree. Plot underscore tree model comma max depth equal to 3. See? If you don't want the text, what we should do? So we have to increase the size. PLT dot figure fixed size equal to 18, 18. Let us see. We should get a tree. Yeah, we are getting a tree here. Or make it 25, 25. We're getting a tree here. And let's see the tree here. You click on the tree and you can see it. But we have to give the feature names. Dot columns. So the first split is happening on average training score. So the first split is happening on average training score. You can copy the image into a larger file and then see it. See here. So see, average training score less than equal to 90.5. Gini is 0.156. Tramples is 5480. Next is KPI estimate greater than equal to that one. You can see the tree here. Copy image. And then shall we put it in some PPT or something and see if we can get a bigger one. Paint. Huh? Paint will be easier. Huh? I don't have paint. You have to get to the paint because in my Mac it is not there. So plot tree is there. Plot tree, the command is this. You can look at the plot tree command. And you can plot the decision tree. Okay. Okay, so I've sent to the notebook. So online guys, I'm stopping the share.
Sir,
Sir, please upload previous class video, sir.
Yeah, I'll upload.
Okay.
Because I have to edit something, so that's why I'm stopping. Today I'll send it. Okay.
Okay.